So we've been talking about ways that we can evaluate limits of functions, and I want to talk about a few rules that we'll have that will allow us to evaluate limits of more complicated functions by simplifying them to more simpler limits. I know more simpler is not the right way to say that, but you get the idea. So what we have on the screen here are it's actually four different rules or properties. The first line is actually two of them together, so that's the sum and difference properties of limits. So you can think of this as the plus here going with the plus here, and the minus here going with the minus here. And essentially, what that says is if we're taking the limit of a function that has the sum of two or more terms in it, or difference, then what we can do is we can evaluate the limit of those terms individually and then add or subtract as necessary. Product rule, same thing. We have in this example here, we're taking the limit of the product of two factors that are going to make up a function that we're taking the limit of. So we can take the limit of each of those individually and do that. The last one, the quotient rule, has a little bit of a caveat here, that when we're taking the limit of a quotient, that denominator should not be zero. If it is zero, then we've seen some examples of this already, where if it's zero over zero, then we have an indeterminate form and we have to do some sort of manipulation to do it. If it's something is not zero divided by zero, then we're going to get some sort of infinite limit. So right, for these rules, we're just going to focus on what happens if that denominator doesn't approach zero. So here's what that means. If we have a limit like this, what we can do is we can break this function right here up into a bunch of smaller pieces and evaluate each of those pieces as a limit, and then put it all back together basically the way that this function is put together. So this limit is the same thing as all of these limits with sums and products and well, there's no difference here, but quotient. So there's the division there. And so just to look at the numerator here, we can split the 3 apart from the x squared because that's a product, and evaluate the limit as x approaches 2 of 3. Essentially what that's saying is what happens to the value of 3 as x gets closer and closer to 2. Seems like maybe kind of a silly question because this doesn't depend on x at all, so that's just going to be 3. And so on. So this limit here is going to be 3. As x gets closer and closer to 2, x squared is going to get closer and closer to 4. We just put the 2 in for the x there. And then in the denominator, this is going to be, first one's going to be 2. As x gets closer and closer to 2, x gets closer and closer to, you guessed it, 2. Hopefully you guessed it. And then as x gets closer and closer to 2, 1 is just staying 1. So this whole piece in here is not something that you would ever write out in a problem, but behind the scenes, when we're evaluating a limit of a complex, and I know this isn't a super complex function, but when we're evaluating a function like this, what we're really doing is breaking it up into those individual pieces, evaluating each piece by itself, and then putting it back together. And then we finish it up here. This ends up being 12/5. So in reality, if we have this limit here, we go straight to the work that I just wrote down there. So we're using what we call direct substitution here and just taking the 2 and plugging it in for x. And we can do that because this is a continuous function, at least around x equals 2. So we can just plug 2 in and we get 3 times 4 over 2 times 2 plus 1, and we evaluate from there. The other property or rule that we're going to talk about here is for composite functions. So remember, composite functions is when we're taking a function of a function. So we're plugging one function into another function. So a composite function might look something like sine of, say, x squared. So x squared itself is a function. Sine of x is a function. And so what we did is we take the x and plug it in for sine of x. So that's what we call a composite function. This property gives us a way of evaluating those But again, like the quotient rule, it has a limitation. So this equation right here is only valid, it only works if the outer function is continuous at this limit right here. And this is actually a typo here. This should say the limit as x approaches c of g of x. Sorry about that. So that goes here and here. So if we evaluate the inside limit, so the limit as x approaches c of the inside function, and f is continuous at that function, then we just use direct substitution to evaluate that limit. If it's not continuous, then we're going to have to do some deeper analysis. We're going to have to look at the one-sided limits. And in the example video that I do, I take a look at a few examples where f is not a continuous function at the value we get when we evaluate the inner limit, and what we do then to look at the one-sided limits and evaluate that.